Hello, for this lesson we are talking about exponential growth and decay, okay? And so this is applications of one of our previous lessons covering exponential functions, okay? So exponential growth and decay, it's specifically talking about situations where it is growing, and again, we're using exponents as a variable. We have exponential growth, so that's a situation where we are growing, right? We're growing in that situation where something is increasing. So an example of that would be your bank account, okay? Or if you invest in the stock market, well actually, I guess stock market could grow or decay. But a lot of times we think of finances when we're talking about exponential growth, okay? Because the longer something is in, say, a bank account, okay, it's going to increase more. And since it's increasing, all right, it increased, a certain percentage. Well, the next time it would increase more because the last time it increased, the amount it's going to increase is going to keep going up and up and up and up. Okay. For another, you might have. Well, we have an example too where that's talking about exponential decay, and that's saying that example is talking about deforestation. Okay, so talking about different neighborhoods or different developments happening, and so the forest is slowly being taken over, but as it's you develop more, you start developing it more and more and more, so more and more keeps being taken away. So let's look at some of this, and I've got a couple boxes here to just help you along. So first, let's talk about the formula. The formula there is y equals a times b to the xth power. Okay. Those values, they're pretty similar. You're going to use the same formula for both exponential growth and exponential decay, but it's just slightly different, okay? And I have it highlighted in that box where the differences are in green for exponential growth, because growth is good most of the time, unless you're... Yeah, most of the time it's good. And then red is exponential decay, and that's where it's decreasing. So let's look at it. A for both examples is the starting amount. So that would be when x equals 0. And remember, anything to the 0th power is 1. And so basically what that means is, after no amount of time. So that's the starting amount, right? So if I put in my money into the bank account today, right, it's not good. They're not going to go, oh, here's 5% for putting it in. No, it has to be in there for a certain amount of time. So it's the starting amount. Okay, and for the starting amount, it must be greater than 0. Okay, so A must be greater than 0, because if your starting amount is 0, you're not going to gain anything, right? If I don't put any money in the bank account, I'm not going to gain anything. Okay, so for B, this is where it starts to be a little bit different. Okay, so B in the case of exponential growth is a growth factor. So what's happening with it? Okay, how is it growing? And B, that's going to be, B must be greater than 1. Okay, now remember, this is going to help us if we remember this rule. All right, so if something is growing, that means you had the original amount. The original amount was 100%, right? If I put $5 in, 100% of what I put in is $5. If it is growing, that means the next time I no longer have 100%, I have more than 100%. Okay? So, for a growth factor, what it's going to be is it's going to be 1 plus, 1 plus the decimal form of the growth factor, so the percentage. So if it grows 5%, let's use that as an example, 5%, you would add 0.05, okay? Or it's going to be 100% plus the growth percent. So if it's 5%, it would be 105%, okay? And then if we did it in decimal form, which is more useful for solving equations, it's going to be 1.05, okay? So remember, if you're growing an account, right, your bank account, then when you earn that interest, you're going to have more than 100% of what you had, okay? Whereas the difference in exponential decay is that it is minus, okay? So let's use that same example of 5%. Let's say it's decaying at a 5% rate. You would subtract it. Okay? Because now, if you had 100%, but you lost 5%, then you'd have 95%. And if we're doing it in decimal form, it would be 1 minus 0.05, which will get us 0.95. Okay, so that will be how you discover what is my growth factor, right? This is the growth factor. And what is my decay factor? That's my decay factor. Okay, x in both situations is just the exponent, and usually it's going to represent time. Right? A lot of times it will represent time in these situations because you'll want to know, okay, if I make 5% interest on this amount of money, it's going to be, how much am I going to have after this many years? How about this many years? All right. But so that's a breakdown of what those variables mean. Okay, so you should have, when you're setting up a standard formula, the A and the B, those are the things you're already going to know. Then they're going to usually have you say, okay, well, what about when it's been this many years? Then you're going to plug in that value for X. So here we go. Alright, so suppose one of your ancestors invested $500 in 1900 in an account paying 5% interest compounded annually. Okay, so that means that compound means that they solve it, right? That it happens annually. Annually means every year. Okay, annual means every year. Find the account balance in each of the following years. Okay, so let's see. First of all, let's see if we can. First, we need to determine: is it exponential growth? Is it exponential decay? And if it is paying 5%, right? They're paying me 5% for having that money in there. So it's growing. We're gaining more money in that account because we are letting them use it. They're giving out loans, making money, and so they're rewarding us for that. So we need the starting amount. Okay. Well, the starting amount was 500. Okay. I've got y equals 500 is my A. My B is the growth factor. Well, we actually already did this because it's 5%, which means I need to add 100% and 5%. That gets me to 105%. When I'm working with equations, I don't want percentage form. I want decimal form. So it's going to be multiplied by 1.05, and then it's to the x power. So in order to solve these, all I'm going to have to do is find, well, how many years have occurred, okay? How many years have occurred in order to find how much will my investment be worth? Or, well, rather, my ancestors' investment be worth. So here we go. For 19, I'm going to use my formula. I'm going to say y equals 500 times by 1.05. Well, how many years has that money been in the account? It's been in the account for 5 years, which means we are going to send it to the 5th power. Okay, so, well, let's solve it out. So this is where, yeah, you're allowed to use calculators. I don't expect you to do all this out by hand. Okay? Okay, and it's to the 5th power. Okay, so that one's going to get me $653.48. Okay, and we're always going to, for this one, we'll round it to the hundredths place since we're talking about money. So $653.48. Well, that's a pretty good investment. I wouldn't mind gaining, $153.48 over 5 years. That'd be pretty nice. Okay, well, let's do it at 1950. So y equals 500 multiplied by 1.05. But we need to determine what power are we going to. Okay. Well, this time it's going to be 50. Okay. So we don't go from what year we last found because we have to remember we said from the very beginning we're using our base number. Okay, the starting amount. So we're going to go 50. Okay. Let's plug that in. 500 multiplied by 1.05 to the 50th power. Okay, that one's going to get me, it's going to get me $5,733.70. I don't know about you, but I'm okay with that growth. Wow. I wish bank accounts did that these days, but they don't. Okay. We're doing it again using the same formula. Well, how long has this money been in? At this point, it's 100 years. Now notice, if you look, I can't just multiply this by 10. Well, 5 and 50, I just multiply that by 10. It doesn't work because this is exponential, okay? It's going to get really big, really fast, okay? So let's go with this one. 500 multiplied by 1.05 to the, this time it's been 100 years, to the 100th power. Okay. I'm going to whistle each time because each time it's beautiful. All right, 65,750.63. So over $65,000. Okay, for the last one, it's, well, really, what would it be worth this year, 2020? Well, at this point, it's been 120 years in the account. Let's solve it out. I am going to get 174,455.99. Okay. So we see this, okay, clearly as this exponent got larger, okay, it quickly grew. And the smaller the growth factor is, the slower it's going to grow. So bank accounts these days, they're not paying you 5% interest annually for the money you have in your account. I wish they did, but they don't. Right? They're paying a very, very small percentage. So if you've got a growth factor of like 1.0005, okay, it's going to grow much slower, but it would be exponential. It would just take hundreds or thousands of years maybe to get to that. Okay, but this one is one that clearly shows exponential, how it grows as the exponent grows. Okay, for 2, it says suppose the acreage of a forest is decreasing by 3% per year. Because of development, if there are currently 3,500,000 acres of forest, determine the amount of forest land after each of the following. So, well, let's set up our original formula. And I'm just going to set it up, let's see, in A. Okay, so I'm going to have y equals, well, what's my starting amount? Okay, my starting amount is 3,500,000. Okay, big number. It's going to be multiplied by, alright, this time it's decreasing, so I need to do my decay factor. So it means I need to do 100% minus, well, it's 3%, so it would be 97%. Okay, I want it in decimal form, so I'm going to multiply it by 0.97, and it's going to be to some value. Okay. So, well, here's the thing. So let's unpack this. All right. Well, if it was to the 0th power, so after 0 amount of time, right? 0 years. After 0 years, that would be 0.97 to the 0th power, which is 1. So it would be 3,500,000 multiplied by 1. Well, that would equal the value we have. So that's correct, okay? And then after 1 year, well, 0.97 to the first power is 0.97. What would happen is we'd multiply this by just under the value of 1, which means it's going to get smaller. Not a lot smaller, but it's going to get smaller, okay? Right? If we multiply a number by 1 or 100%, it's going to remain the same. Since we're multiplying it by, okay, 0.97, it's going to start getting smaller and smaller and smaller and smaller. So we need to plug this in. So for that x, it's going to be 3. So I'm not going to rewrite it out because I don't have space. So I'm sorry. Okay, so I'm going to scribble that out. It's 3. Okay, my formula is y equals 3,500,000 multiplied by 0.97 to the x power, but I don't have space to write it right now. Okay, so let's plug it in. 3. Let's make sure I put in enough zeros. Okay, multiplied by 0.97, and it's to the, for this one it says we're testing for 3, so to the 3rd power, and that's going to get me 3,194,355.5, and it's in acres. Okay, it's a little larger than the 100-acre woods, but we see that it's decreasing, right? We decreased a little over 300,000 acres. Here we go, let's do for 5. So we need to use the same formula. 3, 5, 0, 0, 0, 0, 0, multiplied by 0.97 to the, this time it's 5 years, so to the 5th power. Okay. Multiplying by 0.97 to the 5th power. And we're going to get out the answer. 3,005,569 and I'm going to round to the 100th place. 0.9 acres. Okay, let's do it to the 10th. So we do the same formula. 3, 5, 0, 0, 0, 0, 0. Multiply by 0.97 to the 10th power. It's going to get us and we see it's starting to really decrease. 2,580,984, and we're going to do again the hundredths acres. Okay, so we start to see as time starts to go on, and 10 years by no means is a short period of time, kind of with how we look at it, but for the world, right? If we're talking about deforestation, that's pretty quick. Okay, so we're losing. This has lost almost to this point 1 million acres. Okay, we've almost lost 1 million acres. Now let's do it after 20 years. Equals 3,500,000 times 5.97 to the 20th power equals. Let's see. $1,903,280.2, and if we're running to the hundredths, I'll put the 0 acres. Okay, so there we go. There is exponential growth and decay, walking you through 2 different examples, going through how we're utilizing this, understanding how do we set this up, right? Biggest things, right? Biggest things, understanding, is it growth or is it decay? If it's growth, we need to set up the growth factor. If it's decay, we need to set up the decay factor. Okay? Remember both formulas. The formula is the same. You just need to know, is B, is it a growth or is it a decay? Good luck on your lesson.